Hello everyone and welcome. So in this video I'm going to teach you the squeeze theorem. Okay, so squeeze theorem is a theorem where we can use it to find the convergence of given sum sequences. Okay, some people even call it the sandwich lemma or the sandwich theorem. I will explain later why we call it the sandwich theorem. Okay, so let's learn it. So the theorem is, suppose that xn, yn and cn are given three sequences. So we are given three sequences. We work with three sequences, okay? And they have an interesting relationship. The relationship is that every term of the sequence cn is larger than or equal to the sequence yn, and every term in sequence xn is smaller than or equal to the sequence yn. So xn is the smaller sequence, zn is the larger sequence, yn is in between xn and cn. And not only that, the limit of both larger sequence and the smaller sequence are same. Limit of xn and cn are same. Okay, so the relationship is that given that they have this increasing order, and the limits of the lower sequence and the larger sequence is same, then if that happens, if those two things happens, then they say that the limit of yn is same as the limit of xn and cn, and the limit of all three sequences are same and they are convergent. Okay, so that's the squeeze theorem. Now how do we use squeeze theorem? So the way we use squeeze theorem is that, well, we are given a sequence. Okay, so let's take an example. So let's say we are given yn, like you have to think it like yn. We are given the sequence -1 over n to the n over n. Alright, so given this sequence, so you are given a sequence and you pretend like, well, it's very hard to find the limit of this sequence, so we don't know the convergence or divergence. Okay, so presumably it's a sequence where finding the limit is no easy task. Okay, so let's pretend, okay, we know the limit of this sequence, but let's pretend that it's hard to find. So instead of thinking about the limit of the sequence right away, we think about two sequences where we find a sequence smaller than yn and a sequence larger than yn. And hopefully if the limits of those boundary sequences are same, then the limit of the two sequences are same as yn using the squeeze theorem. Okay, alright, so we want to find a sequence that is larger than -1n over n and a sequence that is smaller than -1n over n. Not only larger and smaller, but also in the sequences that you finding the limit should be also an easy task, right? Otherwise, why do we even use squeeze theorem? So two things. Let me be clear on this. I think I was not clear. So the thing is that you have to find two sequences, a larger sequence and a smaller sequence. Not only that, finding limit should be an easy task of those two sequences. Okay, all right, so think about this. Let's think about the terms of this sequence. So when n is equal to 1, it's -1, and the second term is 1/2, the third term is -1 over 3, the fourth term is 1/4, so it goes on. Now think about a sequence where every term of that new sequence is either large or same. What do you think? How about the sequence 1, 1/2, 1/3 and 1/4? See, definitely 1 is larger than -1, 1/3 is larger than -1, 1/3, and the others are same. So this new sequence is larger than or equal to this sequence, right? What is the new sequence? 1 over n. How about a smaller sequence? Well, how about -1 and -1/2 and -1/3 and -1/4? That sequence. Either they are same or smaller, right? So this sequence is -1 over n. So the two sequences are 1 over n and -1 over n. -1 over n is smaller than or equal to -1n over n, and 1 over n is larger than or equal to the given sequence. Okay, so we found two sequences. We found both boundary sequence. All right, so what is the limit of -1 over n? Limit of -1 over n when n goes to infinity is 0. What is the limit of 1 over n? Hopefully it's the same. Yes, it's 0. So limit here is 0, limit here is 0. So by squeeze theorem, what is the limit of negative 1 to the n over n? 0. So the limit of negative 1 to the n over n is 0. So it is convergent. Okay. So we did not directly found the limit of negative 1 over n over n. But we found two sequences. Using those two sequences and their limits, using the squeeze theorem, we found the limit of our actual sequence. Now this is an easy example. Okay, so if this is a hard sequence to find the limit, which I will present you a couple of examples in the next video. If it is super complicated to find the limit here, it's best to find two boundary sequences, and using their limit, we find the limit of this given sequence. Okay, all right. So let's visualize this. To visualize this, let me give you an example sequence, a little bit complicated one. Sine n over n. Okay, all right. So now pretend that finding the limit of this sequence itself is a hard thing. Okay, just finding the limit directly. So we want to find two sequences. Okay, where one sequence is greater than or equal to sine n over n, another one is smaller than sine n over n. What do you think? Let me show you the trick. Think about sine n. There's something that you always learn in calculus where sine theta is always what? Between what numbers? Negative 1 and 1. That's something that we learn in calculus, right? So sine n is always less than or equal to negative 1. Greater than or equal to negative 1 and or less than 1, right? So we know this. But how about sine n over n? Well, n is a positive number, right? So let's divide the inequality by n. It will not change the inequalities because n is a positive number. So apparently sine n over n is between 1 over n and negative 1 over n. Okay, so isn't that wonderful? What is the limit of 1 over n? 0. What is the limit of negative 1 over n? 0. So guess what is the limit of yn? Sine n over n should be 0 by squeeze theorem. So then this sequence is convergent to 0 by squeeze theorem. We do not know how to find the limit of sine n over n, but instead we found two sequences, xn and zn, right? Okay, so why do we call this sandwich lemma before we visualize this? The sequence that is given to you, the sequence that the limit is so hard to find, is like the meat of the sandwich. Whatever you put inside the sandwich, meat, or if you're vegetarian, vegetables, or egg, or whatever you put inside. So the two sequences, the upper sequence and the lower sequence, you can think it as the bread pieces in your sandwich. Okay, I guess that is why they call it sandwich lemma. I don't know, it's something that I thought of, okay, as a kid. All right, so let's visualize this. So if you visualize this, well, we have sine n over n. We already know the smaller sequence negative 1 over n, and we know the larger sequence 1 over n. So let's look at the table. I mean, looking at the table is not necessary. Oops. Well, I have to execute these. All right. Okay, so let's visualize this. Okay, let's visualize the three sequences. So see what happens. Now here, the green color dots are the terms of the sequence 1 over n. And orange color sequence, orange or this yellow color dots are the terms of the sequence negative 1 over n. So look at these blue dots. They are the sequence sine n over n. You can see they are scattered all over the place, right? So someone would have a hard time finding the limit of sine n over n. But if you look at 1 over n, it's perfectly behaved. You can clearly see that it's going to 0. And negative 1 over n, it's also approaching 0. But sine n over n is always between those two. It's neither exceed or neither go below negative 1 over n or doesn't exceed 1 over n. It's always between 1 over n and negative 1 over n. See, it's pressed between 1 over n and negative 1 over n, right? Sandwich, idea of a sandwich. So sine n over n is also approaching to 0 because they are bounded by 1 over n and negative 1 over n. So that's the squeeze theorem, this sandwich lemma. I guess the squeeze name also makes sense. Okay, all right, so I showed you only couple of easy examples. In the next video I will show you real hard examples, real hard sequences where finding limit is difficult directly, but instead we use the squeeze theorem. Okay, all right, thank you very much. Bye bye.